Good morning.
Good morning, ma.
Good morning, sir.
Thank you, ma.
Yes, sir.
Just to let you know that they are hearing you.
Oh, okay.
Thank you.
All right, sir. So let's
I'm
start.
off.
Okay, sir.
Chat later, ma. Thank you.
Okay, so we've been talking about equilibrium constant. Equilibrium constant, K equilibrium, is product over reactant. Concentration raised to power the stoichiometric number of moles, which is also equal to forward over reverse of the reaction. So in today's class, we're going to look at how it has been applied in some aspects of life. There are many places where it is applicable, but we're just going to look at a little. As you go more in your coursework, you would learn, as you grow more in your coursework, whether medicine, pharmacy, engineering, you would learn the applications quite more. Okay, so we're looking at solution equilibria. Solution equilibria in solution at equilibrium associated with anything dissolved in water. So you can talk about the solubility equilibrium, and you can talk about acid-base equilibria, because acid bases are usually defined in water in most cases. Our body system is made up of about how many percent water? The blood is made up about 70% water. So everything we're talking about aqueous equilibrium is dissolved in water. So one other thing, let's look at self-ionization of water first before we delve into the acid base. Auto-ionization or self-ionization of water. So what is self-ionization of water? So self-ionization of water is if you put water, it can ionize into the hydronium ion or OH ion plus OH minus. In a simpler way, H2O going to H plus OH minus. However, it has long been observed that H plus does not exist like that in solution. It exists as H3O plus. But out of laziness at times, we just stick with that. Anyway, so the appropriate way is H3O plus. So you see, it's 2 moles of water going to H3O and OH minus. The equilibrium constant expression, because this is an equilibrium, the equilibrium constant expression is the concentration of H3O plus times the concentration of OH minus. Because H2O is in a pure liquid form, H2O is not included in the expression. Included. This equilibrium constant reaction for the self-ionization or auto-ionization of water is given the symbol Kw. Like every equilibrium constant, it is temperature dependent. Temperature dependent. So Kw at 25 degrees is given as that. It is called ion constant or water dissociation, ion product constant of water, or water dissociation constant. So because for every 1 mole, every H3O plus is accompanied by that. So if we look at this equation, 1 mole of H3O plus is accompanied or equivalent to 1 mole of OH minus. So this product is like OH squared or H3O plus squared. The concentration of H3O and OH minus must therefore be equal at any given point in time for that temperature. Like we said, it is temperature dependent at 37 degrees centigrade. This is the ion dissociation constant of water. However, most reactions take place at what we call the room temperature, which is approximately 25 degrees centigrade. And that is why this value is constant. This value is usually reported for the water dissociation constant. Okay, so let's take do a quick example. Excuse me. Calculate the values of H3O plus and OH minus at 25 degrees for pure water. We can always calculate it using this value. I'll look at questions in a minute. Remember, this is the expression, this is the equation, formula for the water dissociation constant. So in pure water, H3O plus, or in neutral water, the concentration, so pure means that nothing else is dissolved. No acid, it doesn't mean clean water. Pure water means water only. When you say a pure substance, no other substance is present from the point of view of chemistry. So in pure water, which is a neutral solution, H3O plus, according to that equation, 2H2O going reversibly to H3O plus OH minus. It's 1 to 1, so OH plus is always equal to OH minus is always equal to H3O plus, which means we can simply, so if you represent that by X, then it means that X squared is equal to that. And solving for the square root, we have X to be equal to 10 raised to the power minus 7. And this is the reason, if you recall, when you say the pH, P is a minus log of something. So pH, which is minus log of H3O constant, will give you 7. That's why the pH of pure water is 7. 10 raised to the power minus 7. If we were to calculate it at a different temperature, at 37 degrees, for example, ion product constant for water is 2.5. Mute yourself, please.
Not say anything. Yeah, sure. Okay. Hi.
Adedeji Tobiloba Esther. Okay. So the dissociation, so recall that this is for neutral water again, so which is X. So using the same formula, X squared will be the square root of this. So we have it as 1.8, meaning that we have more of the dissociation at higher temperature. Okay, so another application that we can see is in the dissociation of weak acid. Acids dissolve in water to give H3O plus. That's the Arrhenius definition and Bronsted-Lowry definition. So a little different for the Lewis acid. So we're not going into that. You've talked about acids and bases. We have strong acids And we have weak acids. Let me write it on the side. Strong acid, if I call it HS, it means it dissociates completely in water. So the ions are not in equilibrium. Ions are not in equilibrium. But for weak acid dissociates partially. Dissociation, giving us a weak acid to be call it HA, a typical weak acid. It still gives us the H3 plus A minus. A minus is the conjugate base. So it is in so simply, so let's just remember this is not allowed. Technically, it doesn't exist. H plus. So H3O plus. The dissociation equilibrium constant for this expression, a weak acid dissociates in water to give H3O plus its conjugate base. It is in equilibrium with that. So equilibrium constant expression is given as H3O plus A minus, and H2O liquid is not in the expression. There was one concept that we discussed last time, chat. Okay, good question. See her flying because of test. You don't even know what to type here any longer. You're typing private messages. So let me not be bothered whether you understand or not. So a weak acid dissociates partially in water. Hence, the concentration of H3O plus is not necessarily equal to the concentration of H plus, even though it's a 1-to-1 ratio. Not all the H plus has been dissociated in water. How do we obtain the concentration? We use the ICE method that we discussed in last class. So imagine originally you start with Y moles of H plus. So at the initial stage, there is no H3 plus, there is no A minus. However, at equilibrium, H plus has reduced from Y. Equilibrium, HA has gone from Y to Y minus X. That's how much of it has dissociated. So if we look at the equation, so it's a 1-to-1 ratio. So if X has been released, it means that X has produced H3 plus and X has produced A minus. The equilibrium constant for this dissociation is H3 plus A minus. It is called the acid dissociation constant and given the symbol K sub A. So A to indicate acid. Remember for that of water, Kw is to indicate that we are dealing with water. So if we use this, which means our equilibrium concentration for HA is Y minus X, for H3O plus is X, for A minus is also X. So if you slot it into the equation, that's X times X over Y minus X. And you have X squared equals to Y. Usually for most acids, Y is so much greater than X such that Y minus X is approximately equal to Y. So if we put it at that, that means that we can write our Ka to be x squared over y. And remember, and see, we're trying to look for the concentration and pH of a weak acid. So if you make x the subject of the formula, so you bring y to this side, x is squared, square both sides, so you have xy squared. And you know, x is the amount of H plus concentration that we have in the solution. So we can have that pH is minus log. Recall that when you say P is minus log of whatever is in front of it. We can calculate pOH, we can calculate pKH. So let's do an example. So this is our important equation. Please note that equation. That's what we use to calculate the pKa, pH of the weak acid. Any question? No question. So let's look at the example. The example is calculate the pH of 1.02 mole of ethanoic acid, which has a dissociation constant of this. So usually it's good to always write what you have. You have pH. We have to calculate pH. You have the concentration of the acid, given to be 1.0 times 10 to minus 2 mole per dm cubed. And the pKa, sorry, Ka is 1.76 times 10 to minus 5. Even though its unit is given here, the unit is not necessary. Acetic acid, that which is ethanoic acid. Ethanoic acid is also acetic acid. That's the formula CH3COOH. If you put it in water, pure liquid, it dissociates as H3O plus plus the conjugate base. The equilibrium constant, which is the dissociation constant, has the formula CH3 times H3O over HCOH. Again, H2O liquid is not included. And C, so from the last slide, X equals the square root of Y times Ka, where Y is the initial concentration of the acid at the beginning. Ka is given in the question, so we can easily solve for H3O plus, which is the square root of 1.76 times 1.0 times 10 raised to the power minus 2. We put that into calculator, we should observe, we should have that value. pH, that's the formula for pH. pH is minus log. Log is logarithm. So if we put this in, substitute for H3O plus, the pH of our solution is given as H3O plus. Why is H2O not included? Somebody is asking, why is H2O not included? Any other question? No question. So H2O is not included because it's in its pure liquid form. If you recall in our last class, we said any substance in liquid and solid form, their concentration are not included in equilibrium constant expression. So we'll look at more examples as we move on. A strong base, we can also calculate the pH of a strong base. So the value of pH tells us basicity and acidity of a system. Okay, first, a strong base dissociates completely and a weak base dissociates partially. This is a strong base. This is a weak base. The common strong bases that we would encounter are I think the common acids, strong acids, HCl, HI, HNO3, H2SO4, HClO3. There's one or two more. That's every other acid other than this one are not strong acid. Anyway, so that one is easy. To calculate the pH of a basic solution, first thing is to calculate OH concentration. We can relate OH. We remember that is Kw, so we can always relate them together. And once we calculate pH, then we can calculate, if we get OH minus, we get POH, and then we get pH, which equals to this. Now, how did we arrive at this? At pH being equal to, let's do a quick one here. So recall OH minus times H3O plus is Kw. At 25 degrees centigrade, Kw is equal to 1.0 times 10 to minus 14. So OH minus H3O plus is equal to that. If you take the minus log of everything together, so that would be minus log OH minus log H3O plus, that's equal to minus log 10 to minus 14. That's log 1 is 0. So this is POH plus pH, that's equal to 14. So that's why we arrive at this. Okay, a quick one. Calculate the pH of 1.2 molar NaOH. NaOH is one of the strong bases, meaning that it dissociates completely. It goes straight to OH plus Na plus. So we have 1.0, so OH minus. If it dissociates completely, it means that the concentration of OH minus is equal to the concentration of the initial base. So you can now calculate the pOH, and remember that our pH is 14 minus 2. 14 minus pOH, so that gives us 12. The one that I'm interested in is the, please, re-explain what? I don't know. You have to be specific, please. You said re-explain. I'll explain many things. Re-explain how to calculate X. You know, I noticed a lot of you were not in class on Wednesday. So that was really thoroughly discussed on Wednesday. Today is my last class. I'm not sure we can go through all the ICE table. 12. Thank you. Somebody said, please re-explain. I don't know what I'm to re-explain. So calculating X again, let's look at this slide, whether we will get it. Weak bases dissociate weakly. because they dissociate weakly, this is their own dissociation. It is called base dissociation constant. For the ammonia that we had the other time, NH4OH going to NH4 plus OH minus. So KW would be KB, sorry. KB would be NH4 plus times OH minus over NH4 OH. Okay, so the pH is also determined from OH minus. Let's work an example. So I hope that this example will let us understand the concept of X again. We are to calculate the pH of 0.15 molar solution of NH3. Now, let me explain the concept of this table. This table is called ICE table. It helps you to tabulate your different concentrations. It's just a way of keeping track. You don't have to use it, but it's a very good way of keeping track of the things we are dealing with. So how is it constructed? You look at your species. Here, NH3 plus NH2, that's ammonia, plus H2O liquid goes to NH4 plus OH minus. So the things that we have, the species that we have with varying concentration is NH3, NH4, NH3, NH4 plus, and OH minus. H2O is approximately constant. Initially, for example, let's see, initially the concentration is 0.15. At the initial stage, these ones are 0 and 0. At equilibrium, what's the value? Because it's the equilibrium value that we use to calculate our equilibrium constant. Kb, even if it's called basis dissociation constant, it is an example of a dissociation constant. So this dissociates, some of this dissociates, so there's a change that happens, which we call X. So what you have at equilibrium is 0.15 minus X. If X dissociated to give NH plus and OH minus, that means using a ratio 1 to 1, one of this goes to one of that and one of that. It means X most of this must have been produced, X most of this must have been produced. That's the change. Now our total equilibrium concentration. So equilibrium concentration will be the addition of those two columns, I plus C. So 0.15 plus minus X, we get that. X 0 plus X, 0 plus X. So we have just called this a change in concentration. It is further explained in the notes that has been sent to you. Okay, so because it's in most cases, especially if it's more than 5, it's usually very few that is dissociated for weak acids and weak bases. So we used Y in deriving that. So usually X is so small that we have it as 0.15 in the end. Okay. In the last example, we're looking at weak acid. X was H concentration. Now we are looking at weak base. So X will be concentration of NH plus or concentration of OH plus, OH minus, I apologize. So if X is given by that, we can write that our Kb is X times X divided by 0.15. Let me see. The classes on Wednesday usually clash with a particular course. That should have been complained. So this is already almost the end of the class. Oh, sorry, you don't have this slide. I apologize for that, but it is in the notes. You have it in the notes. So if you want to follow with the notes, let me try to see what page we are in. I don't have the notes with me here. If you want to follow with the notes, I think we are on page 26. That's for weak acids. For weak bases and weak bases, we should be around page 29. 29, 30. But I promise I will send the slide. Chemical. The reaction table is not really clear. Please, can I get clarification? Reaction table. This table. Okay, I just explained it again now. I hope you get it. When you're given substances at the beginning, again I said ICE is a table. We're running out of time on 9:30. ICE is a table to tabulate your concentrations of your species. The number of species that we have will determine how many columns that you have. In this example, we have NH3, NH4, NH, NaOH. I hope if there's time, maybe I'll go back to the slide of last class, and then we'll see it. So you have initial concentration that was given. Initially, we're given 0.5 mole NH3. It is NH3 that gave the other ones. So it is possible, if it's not a dissociation like this, if it's possible in a regular reaction, you could have the product introduced anyway. So at the initial stage, there was nothing of this. So that's why this is 0. We were not given equilibrium concentration, but we can approximate equilibrium concentration because we know we are dealing with a weak base. So equilibrium concentration typically should be 0.5 minus how much of this has gone into the reaction. So if we say that X has gone into the reaction, it means that it has reduced by X. So that's why we have minus X. If X amount has reduced, it means that X amount has produced the product. 1 mole of this gives 1 mole of NH plus. So it means that X moles of NH3 gives X moles of NH4 plus. Similarly, 1 mole of NH3 gives 1 mole of OH. Therefore, X moles gives X moles. Now, the sign is negative here because it is reducing. The sign is positive here because it is increasing. In the last row, which is the equilibrium concentration, it is usually summation of the two above rows. So these will be 0.15 plus minus X, which is 0.15 minus X, 0 plus X, X, 0 plus X, X. So our equilibrium concentration should be 0.15 minus X, X, and X, meaning that the equilibrium constant should be Kb being equal to X times X divided by 0.15 minus X. So usually, all of this is born out of several observations. So usually for weak acid and for weak bases, in most cases, not in all cases, the X is usually small compared to the initial concentration. So if that is the case, it means 0.15 is so much greater than X such that 0.15 minus X will still give you something about 0.15. So 0.15, that's still about 0.15. So that approximation holds. And since that approximation holds, so Kb becomes X times X over 0.15, which is what we have here. We're given the value of Kb from the equation. So that is this. So our x can be calculated. So you see, we still arrive at x being equal to the square root of y times kb, similar to when we're calculating for acid, y times Ka, where y is the concentration of acid for weak acids, and y is concentration of base for weak base. So substituting, so x, which is square root of 0.15 times Kb, substituting that value, we can calculate our OH concentration. Apologies, POH should be minus POH, so this should give us 2.8. Therefore, our pH is 14 minus 2.8, which means we have assumed that we are working at 25 degrees centigrade. Thank you. Mayowa Thompson. All right. There's a relationship. Let me see, do I have time? There's a relationship, I'm going to move fast, between the Ka and Kb of conjugate acid base pair. Remember the concept of conjugate acids and conjugate bases. So an acid dissociates in water to give H plus and its conjugate base. A base dissociates to give OH minus plus its conjugate acid. So H3 here, what is it? NH3 in water to give NH4 plus OH minus. So we have the Kb, it's a base. This is its conjugate acid. So if conjugate acid, if we now take that conjugate acid, so consider the conjugate acid, not conjugate base. So if it's NH4 goes into plus water, we should get NH3 plus H3O plus. So this is the acid dissociation constant for. So let's call this equation 1 and call this equation 2. If we add the two equations together, okay, so that's been corrected here. So NH3 cancels NH3, NH4 cancels NH4. So here we now have H2O, 2 of that, plus OH minus, plus H3O plus. And recall one of the properties of an equilibrium constant. If you have two steps, the equilibrium constant is a multiplication of the equilibrium constant of each successive steps. So if you recall, this is equal to the ion dissociation constant of water, meaning that the product of the acid dissociation of an acid and the conjugate base is the water dissociation constant. So therefore, if you know Ka, Kb for NH3, you will know Ka for NH4 plus. These are some examples. Quick calculation. Given Ka for HF at 25 degrees centigrade, calculate Kb for F minus. We know that HF goes to H plus F minus plus H2O, H3O plus F minus. I write it on the side. HF plus H2O is a weak acid, H3O plus F minus. This is our acid. This is the conjugate base. So this is straightforward. All we need to do is recall this formula. Ka, Kb, not for everything, but for a conjugate acid base pair. So since we know at 25 degrees, Kw is 1.0 times 10 to minus 14. So we have our conjugate. Yes, Nelson, you are correct. Okay, another application, we mentioned 2 applications. So the solubility of ionic solids. Ionic solid dissociates in water if it is soluble, it dissociates completely, like NaCl. Put it in water, it dissociates completely, Na plus or Cl minus. You still have your water somewhere there. A saturated solution, so but there are some, I think, to saturate sodium, you cannot go and try it at home. How much water do you need to dissolve 100 grams? Anyway, so it is possible that when you dissolve ionic solid, it goes into water as ion. But at times, not all solids dissolve. I'm sure that if you try to put carbonate soda or soda inside water, you don't see anything dissolving. There's little, not the amounts that you use to dissolve alum is also limited. Anyway, that's by the way. So some solid, for example, AgCl, goes into water and does not completely dissociate, meaning that the ions are in equilibrium with the solid. Equilibrium constant expression for this is aqueous, and AgCl solid is not included. So somebody asked the question the other time, it's not included because its activity is 1, or in general, solid and liquid have activity that is constant. So it's not varying. Equilibrium constant for solids like this is called solubility product and is given the symbol Ksp. It varies with water just like the equilibrium constant. The solubility product, so we've seen Ka today, Kb, Kw, and there is another one, Ksp, the solubility products. You can write solubility products as given. It's just that writing solubility product is very straightforward. The equilibrium constant for a slightly soluble ionic salt, that's the one that I use to write equilibrium. Just as long as you are able to write the dissociation. AgCl dissociates. Please, it's important to put the solid when you start to work more. It is important to write steps of what you're dealing with. So I want to believe that we are familiar with that. Ksp is that Hg2 plus Cl2. This is where it can be tricky. This is Hg1. That's how mercury exists, plus Cl2. So you have concentration of Hd plus in the oxidation state of 1 and Cl minus raised to power 2. Similarly, Pb, 3Pb going to 2. So Pb plus raised to power 3, ASO4 raised to power 2. Why have so many mistakes? Now, how do we calculate solubility products? Okay, I will resend the notes. Omole. Any other? Yes, I will resend the notes. I can't resend the note at the moment, please. I will resend the notes and the slides, the complete slide. So let's calculate solubility product. Calculate the KSP of 0.2 molar Ba2 at 25 degrees centigrade. BaCl2 dissociates as follows, which means we can simply write BaCl that. So KSP, the solution says is 0.2 molar, which means the ions that have, that's the amount of ions that are dissolved. Concentration is 1 to 2. Cl will be 2 times 0.002 molar. So we put it in the equilibrium constant expression, solubility product expression. Punch in our calculator. That is the KSP of BaCl2 at 25 degrees centigrade. Another example, calculate KSP of 0.01 molar at 25 of Ag2, that's silver chromate, disilver chromate or silver dichromate, one of them. So the trick is that it's important to know how your metal solid dissociates M plus S minus. That is the important thing to note. And then you look at, this is 2 moles of that, 1 to 2 to 1. So the concentration of Ag plus is 2 times 0.1 molar, which is 0.02. The 0.1 molar solution, and the concentration of chromate is 0.001 molar. Substitute into that equation and we arrive at this. Solubility product is very useful in, like we just, in calculation of solubility and in what we call precipitation experiment. Precipitation experiment, people trying to clean environment need to know what they can precipitate out of different environments. The solubility of a substance is the amount of the substance that is dissolved to form a saturated solution. You know, saturated solution is how much the water can take. You can have an unsaturated solution, which means the water can still, the solvent can take more of the solute that you want to dissolve in it. When it is saturated, that's the maximum solute that they can take. Then you can have a super saturated solution, which is with the case of our insoluble salts, most of our insoluble salts, you've already dissolved as much as you can take, and the others remain as precipitate. Solubility is often expressed as mole or mole per liter or grams of the solute per liter. Anyway, we can use solubility to calculate we can use KSP to calculate the solubility of our solution unitless because we're dealing with affinity. Anyway, so how do you calculate solubility? You calculate solubility, you write the equation. Let's just work the example. We have this on the slide. Thank you, getting clearer. I'm glad. Okay, for this salt, for this ionic solid, the KSP is given as 1.6 times 10 to minus 19. What is the molar solubility of the salt, the ionic solid? So calculation includes you write the equation for the equilibrium and its aqueous ion form. The slide that I just went by now, that I just said we don't need to read through. I'm following the steps on that slide. CuOH dissociates solid as given. So the equilibrium solubility product is also as given. If you look at this equation, this is 1 to 1 to 2 mole ratio. But from the equation, OH minus is equal to 2 times Cu2 plus. So we are writing the equation of dissociation, figure out what the expression for the solubility product, and identifying the mole ratio so that we will be able to slot it in. So if that's the case, we can substitute this for that in that. So we have that Cu plus is 2 times Cu times 2. So that means Cu, let's see this, 2 times 2 squared, sorry. Cu2 plus times 2. So we are slotting this value for OH minus squared. So 2 squared is 4. Cu squared is Cu squared times another Cu. We have 4 Cu cubed. So if Cu, that we have, you can make it the subject of the formula. And then you arrive at, so that's 4sp over 4 cube root. KSP is given from the question. I hope I have time for one more example. And the solubility of the salt, sorry, Cu is equal to that. Okay, so this last line, it's 1 mole to 1 mole. We are looking for the solubility of the salt, how much of it goes into solution. The solubility is this 1 mole of Cu gives that. So you're looking for the same with 1 equimolar ratio. If you want to go from 2H, so you divide it by 2. So OH concentration will be 2 times 3.4 times 10 to the minus 7. We have 6 more minutes. So this is something similar. I'm not going to work this example. I want to quickly talk about this. We said we can use KSP to talk about precipitation. Precipitation, experiment reaction, means that you have a solution and then you have solids precipitating out of it. So how is that related to KSP? The value of KSP, so the higher the value of KSP, the more soluble the salt is. If you consider it, KSP is directly proportional to the concentration of the dissolved ions. So KSP, let me write it properly. Dissolved ions. So the higher the value of KSP, the higher the value of the dissolved ions. If you have that much dissolved ions, so let's see, AB solid going to A plus plus B minus. So if you have more of this, it means that more of this has been dissolved. So the higher the value of KSP, the more soluble the salt, and vice versa. In a precipitation experiment, the precipitate. So in a precipitation experiment, you are trying to mix things together and you want to know if you would get out a precipitate or not. So we go back to our old friend, the reaction quotient Q. Q has the same expression for KSP, but it is not calculated. It's not necessarily. So Q is not necessarily at equilibrium. Unlike KSP, which must be calculated at equilibrium. So two things can happen. If you know the concentrations of the ions that you are adding, you calculate Q. So let's quickly work an example and compare the value to the KSP of the salt. As an example, I'm going to take like 5 minutes of your time. Will a precipitate form when this of PbNO3 is added to 0.2 liter of Na2SO4, given that KSP of PbSO4 is that? So at least for what we are saying, we already know that PbSO4 does not dissolve completely. Okay, so the aim is to calculate Q for this concentration that we're given. We know that in solutions, once this go into, so let's see, PbNO3 will give Pb 2 plus NO3 minus. NaSO4 will give Na plus, those are the ions, and SO4 minus. We know that, so we're looking at possibility of formation of this from solubility rules, which we have done earlier. NaNO3 is soluble, but not PbSO4. Even from the question, we can deduce that. So what we need to do is to determine whether PbSO4 will precipitate. So we need to calculate Q, which is Pb 2 plus times SO4 2 minus. Let me explain this part again. If we want to calculate Q for PbSO4, we know that PbSO4 will dissociate as Pb2 plus SO4 2 minus. Equilibrium constant expression is Pb2 plus times SO4 2 minus. This is also the way we are to calculate Q. It's just that if KSP is for equilibrium, Q is at any point in time. Okay, so let's calculate Q. What is the concentration of PbSO4, Pb and SO4 2 minus? At equilibrium. Okay, so let's solve for Q. How do we calculate Pb plus that was dissolved? It said that 0.5 liter of 2.5 mole of PbNO3 was dissolved, added to 0.2 mole. So the total volume that we have in our system now is 0.15 plus 0.2, that's 0.35 mole. I apologize for writing on this, please. The total amount of Pb2 plus ion that was brought into the solution is 3.74 times. How did we arrive at? Molarity is number of moles times volume. So number of moles is molarity times volume. Molarity is 2.5 times 10 raised to the power minus 3. Volume, initial amount that was brought, is 0.15. But the new concentration now in 3.5 liters is 3.74. That's the number of moles. The new concentration is 1.0 times 10 to the minus 3. In a similar way, for SO4, we calculate the amount that was brought in, which is using this formula now, N equals molarity times volume, 0. This times that, and its molarity after mixing going from 0.2 liter to 0.35 liters is now 2.9 times 10 raised to the power minus 4. So if you notice, I have used PBO to tell us that we are not necessarily working at equilibrium condition. So let's calculate Q. Q is PB2 plus, again, so to indicate that not necessarily working at equilibrium. So, okay, sorry. Let's calculate. So if we put so we're going to calculate with the values that we have. 1.0 times that, and it gives us 2.5. Now we need to compare this to our K. K, this is 1.8 times 10. 2.5 times 10 to minus 6 is greater than 10 to minus 8. So it means precipitation will occur following the law that Q less than K, no precipitation. Q greater than K, no precipitation. Q equals to K, we have a saturated solution. Okay, I think the other things are something that we can read. The things that can affect solubility, I'm not sure that's the scope of that's the scope of this complex science. Just like what we just, let me see, any question? Yes. How did Cu plus become root? That means the KSP of an insoluble salt. So I am not going to say that the KSP of an insoluble salt is 0 until you test it and know that that none of it has dissolved at all. To a large extent, everything dissolves, but it's just that some dissolve very small and some do not dissolve. But I don't understand that, but from the equation parts, I like using the method from last equation represents, okay. I wish I could use another method to solve it. If you can find another method, fine, but I don't have time to discuss another method. How did Cu2 plus become cube root? Okay, so it wasn't the same person that asked that question. Cu2 plus became cube root because we used its expression to determine that of say OH and BCl minus. I don't remember. Okay. No more questions. So I think with this we have come to the end of equilibrium and its application. I wish you all good luck. Anyway, if there's no more questions, again, I will send. Don't worry. I will send. It will be sent the way you get the normal slides. Thank you.